And so as we continue on our journey through chemistry, one of the first things that we're going to have to look at is how did we get to modern day? In other words, did we always know about things like atoms or protons, neutrons, electrons, etc., etc.? And so the answer is absolutely not. It was actually pretty backwards for a long time. So in the beginning, right? Way back when, you probably heard of, during the Middle Ages, these people known as alchemists. And so what alchemists were trying to do is that they were in essence trying to turn lead to gold. Now, along the way, many a workshop got blown up. A lot of alchemists lost lots of fingers. But what alchemists started doing, unbeknownst to them, was that they started to realize that by playing with ratios of matter and amounts of matter, we could create new substances that didn't start off from their original reactants. Along the way, for example, alchemists discovered things like gunpowder, or better known as black powder during the time, which was great. But the problem that most alchemists ran into is that alchemists were not following a scientific method. So it was literally a lot of, here's old Uncle Willie's recipe for making black powder, right? And maybe it worked, maybe it didn't, why it worked, why it didn't. There was really a lot of guesswork. It was almost like everyone had their own proprietary blend. So as we move forward through time out of the Middle Ages, as we move away from like the Greeks' idea of there were four basic elements to the body of earth, fire, water, and air, as we move away from that, we start to enter into the age of rationalism, and we start to come to this idea that there has to be a better way of recording and observing our results so that as we compile information over time, we can actually see where we're going. And so as we move into this new age, we introduce the scientific method. And again, you probably learned about the scientific method back in elementary school, middle school. And all the scientific method shows was a way to reproduce the results. So you'd start off with, here's my hypothesis, this is my idea. I'd create an experiment where I could test that idea, and I would collect data so that if everything worked, then in theory, it didn't matter if you were Susie or Billy or Joey, any one of those could take your same data, your same experiment, reproduce, and get the same type of results. So the grandpappy of modern chemistry was a gentleman by the name of John Dalton. What he does is he had a lot of spare time, and he was really interested in understanding weather patterns. He was a wannabe meteorologist before there was such a thing as meteorologists. And so what he realized is that in order to understand weather patterns and phenomena, etc., he has to start learning more about some of the gases that are in our atmosphere. So he starts to learn more about how nitrogen and oxygen, some hydrogen, and how all of these things interact with one another. And so his great claim to fame is that Dalton was very meticulous and neurotic in his data collection. So this is a gentleman that every morning would take the temperature and atmospheric pressure and would do it again at noon and at dinner, and would do this for years and years and years on end. So at the end of it, after he compiles this mountain of data long before computers ever existed, what Dalton starts to see is that there are some patterns that begin to emerge and certain things that he's able to start predicting. Now, let me be clear. This is a monumental improvement because he is the first person to apply scientific method and scientific principles to the study of matter. Yay! But we still have a long way to go. So you get an idea, Dalton is doing his work around the 1700s. So this is not that long ago. It's not ancient history, but it's definitely been a hot minute. And so what Dalton, in essence, comes up with is he comes up with 4 postulates, or his 4 cornerstones as to how matter interacts. Some of these you're going to recognize are going to make perfectly good sense. Others you might look at and go, I don't know if that's still true. So first and foremost, the first big, cornerstone of Dalton's postulates is that all matter is made up of tiny, now here's the kicker, indivisible particles called atoms. In particular, what he really discovers is that an element is made up of these tiny indivisible atoms. But you should already hear in that and go, wait a second, if they're indivisible, what about something like a proton or a neutron or an electron? I've heard of those things. And unfortunately, back in 1700s, Dalton had no idea of subatomic particles. But what he does say is that, an element is made up of tiny indivisible particles known as an atom. Now, here's his next postulates. He says all atoms of the same element are identical. Well, it's great. It's brilliant for 1700, but what we now know to be true is that different elements have different number of neutrons. You may have heard of these and learned about these way back when as isotopes. So unfortunately, while there was a lot of truth to that yes, for all intents and purposes, all atoms of a given element are going to behave rather similarly, they are technically not identical. Third postulate. Elements combine together in simple whole number ratios to form compounds. This third postulate is ginormous. With this third postulate, we are able to finally begin to study and understand how matter interacts. Because what Dalton has clearly paved a path for us, and what he's shown us is that no matter what, there is a ratio that has to exist between atoms and molecules. Reactants and products, right? They have to come together and they combine in these simple whole number ratios. So what we're going to start to see as we move on in our understanding of chemistry is that oftentimes we will make a statement like one of these for two of those, right? Or I needed 5 of these and these 5 produced 2 of those, right? So these are all statements that we will start to see more and more often. And even though it's very basic, and it's very rudimentary, this third postulate does get the ball rolling for modern day chemistry. We actually learn a lot about chemical reactions and processes, still understanding these fundamental postulates. And finally, number 4, and this one's a big one, you've heard of this as matter can neither be created nor destroyed. And so what Dalton realizes is that atoms are neither created nor destroyed in a chemical process, which means whatever you start off with, you're going to end up with it. It may not be paired exactly how we first saw it, but it is still going to have to be the exact same amount. So with Dalton, we get the proverbial ball rolling into modern chemistry. Through Dalton's work, we're finally able to make comparisons in ratio, and this is the foundations of all modern chemistry. And it was so powerful that his postulates stood around for almost about 200 years, not quite, but 100 years plus. And we learned a lot of chemistry during that time. But somewhere towards the late 1800s, scientists had started to realize that all of Dalton's postulates didn't quite make a whole lot of sense. There seemed to be some issues that we were having with it. In particular, around the 1800s, we have a lot of scientists now playing with electricity. And once scientists start to play with electricity, fun fact, while they are able to understand the laws that govern how electricity travels and flows and moves, if you would have asked a scientist in 1810 or 1820, well, what exactly is electricity? The answer would have been, They didn't know. They didn't know what exactly it was other than this negatively charged current. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.